Right. So now that we've discussed the high levels of training, we in this video we're going to discuss briefly what exactly are we training here? What is this model that we are trying to train? So in this video, we're just going to briefly look at the transformer architecture, what it looks like. In architecture, yeah, I think that's the spelling. In upcoming videos or upcoming chapters, we are going to deep dive into it. But like I mentioned, this chapter is just dedicated to the high level details. So we know that these transformers, they are deep neural networks, right? That's one thing we know because Gen AI is part of deep learning. So um, these are deep neural networks. Many of them with billions and billions of parameters, and they were introduced in a paper by Google called "Attention, Attention is All You Need." Attention is all you need. In 2017, that's when they introduced this new architecture. In 2017, it's a very good paper. If you want to read it, just Google "Attention is All You Need." You find the PDF there. But to simplify what they actually said, because what they had was much complicated. So if I'm to show you, let me quickly get the image from the paper, and that was actually a simplified version of what it looks like. We're going to build we're going to build the the transformer in a later chapter. But this is a screenshot from their paper. That attention is all you need, and you can see parts that are called encodings, and then the decoder, the the decoder parts. And let's just move this there. Okay. Just going to change my tool to the pen so we can get into simplifying this. Even though you do not understand exactly what is going on here in their paper, do not worry. Let's try simplify it. Let's try simplify. So what happens is, let me see if I have enough space. Yeah, I think I should have enough space because I'm going to draw like they had. So, for example, if you have a text like this is an example. So that is the text that we have, right? What happens is this is that's what we're calling the input text. So this is the input text that we have, which is this is an example. And imagine that our task here is to do translation. We want to translate from English to German. We want to translate from English to German. That is our task here. So this is the input text, right? It goes through some pre-processing steps. It goes through some pre-processing steps here. And we are going to see what these pre-processing steps are when we are getting into the stage of training and all of that. For now, just know that there are some pre-processing steps that happen. And after those happen, the the result is fed into what is called an encoder. Don't worry about it now. I emphasize it. Don't worry about it now. We'll see all these parts later. So it gets into what is called an encoder. And the encoder, it has access to this whole text. It has access to this whole text, the input text. And what it does is it produces text embeddings that are going to be used later. So what it produces, this encoder, are text embeddings. So you see why I wanted to have to make sure that I have enough space. So this produces what are called text embeddings. These embeddings are vector representations of the text that we put in. So these are vector representation vectors. You've probably by now heard about let's embed this text. Let's use the embedding model from OpenAI or whatever it is. Pretty much that's what we're trying to do here. Converting the text, the input text from words into embeddings, which are vectors, and these vectors are numbers. And we'll see them later. We'll see them later in a later chapter. And when we have produced these embeddings, they are then passed on to Now, let me actually put them in line so it becomes easier to follow. So they are passed on to the decoder. So this right hand side is where the decoder is. And what the decoder does is it sees these embeddings coming in, and it has already it has its own input text. So the input text here could be what has already been translated. So it is, I'll just put input text, and that input text that has already been translated, or it could be zero if we are starting the translation now. We're starting the translation now. We haven't translated any bits of the text. It will be zero. But this will also have its own pre-processing steps, and the pre-processing after being pre-processed gets into the encode into the decoder, and the decoder generates text one at a time, one word at a time. So what the decoder then does, when it gets these embeddings, it then generates text, the translated text, one word at a time. And here we'll have some output layers. We have some output layers. We're actually going to build some of these layers and then you'll see them at work. Output layers. And then when it's done translating one word at a time, it might write something like, I, I will not try offend people who can speak German by pronouncing this, but I'm just going to write it down. So that is the translated text, but it does it one word at a time. One word at a time. So that is the process that Google proposed, or the architecture that Google proposed here. We are going to see all these normalization layers, these feed forward layers. We're going to see the attention layers, but just know that this part here, they are they are showing the encoder, and on this side here, they're showing the decoder. They're showing the decoder. We are going to look at all these positional embeddings here. So our inputs come in, they get into the encoder, they get into pre-processing and all of that, and the encoder side would then create embeddings, and those embeddings, as you can see from this line here, those embeddings are now fed into the decoder. They come through here, plus its own the ones that have been done before, if it has translated before, because maybe it has already written das. So for the next run, the input text would be das, and then it would decode to try finish with word by word with ist and b spell. I think that's what it is. I'm sorry, I'm not German, so I can't really pronounce it. But pretty much, I just wanted to emphasize that this is the simplified version of what a transformer model is. Input text comes in, it's processed, the encoder creates embeddings that are then passed on to the decoder. So these transformers, the ones that the transformer architecture that was proposed by Google, it had an encoder plus a decoder. And this decoder section, encoder and decoder section. So the transformers are pretty much that. Transformers, they have the encoder and decoder sections there. The encoder module, it processes the input text and encodes it into a series of numerical representations, or the vectors. That these vectors, they capture the contextual information in that input text. Then the decoder takes those encoded vectors to generate the translated text. So from the numbers, then to decode or to generate the text in the target language that they want that you want. In this case, it was German. These encoder and decoder, they are composed of many layers, many neural network layers, and you will see them. We'll build them, and then you see in code what these layers actually look like. And they also have what are called self-attention mechanisms. Self-attention, and they're connected with a self-attention mechanism. Those layers. This self attention mechanism is very, very critical. This is the critical part of transformer networks. This critical part, it allows the LLM or the large language model to weigh the importance of different words or tokens in a sequence. So, like I mentioned in one of the videos prior, we could have something like this. London is a city in the UK. It is very, and we want the next word that we want to predict. So the self-attention mechanism might put lots of weight on London, lots of weight on is, lots of weight on city, ignore the rest. Then it will just say London is city with lots of weights here because it's paying attention, much more attention to those three. And then here, just say London is. Okay, I think the one that I'm going to predict here is beautiful through that self attention. And we are going to code the self attention, and you see how it's paying attention to different parts of the text. It doesn't weigh the text, the words similar weighting. No, it doesn't. It has to do that that weighting. So this mechanism, this self-attention mechanism, it allows the model to capture long-range dependencies because maybe it has paid attention to London, which is far from where it's predicting, but because it is paying attention to it, it keeps it. I'll just say in memory as if it's a brain, but but yeah, you get the point. The self-attention mechanism, it allows it to capture long-range dependencies and contextual relationships within the input data which helps it generate more coherent text, like in this case here. If there was no attention mechanism, it might not create text that makes sense based on what has come before it. Previous architectures tried to do that, like recurrent neural networks, but they didn't scale well. They were not scaling very well. But the transformer network, because of this self-attention mechanism, it scales quite well. Well, in long text. I think you have done that with ChatGPT, and you're amazed. It looks magical. How does it know all this stuff that I mentioned a long time ago? It's because of some of that self-attention mechanism that is in there. So other variants of the after this vanilla one, the transformer model that they built, they created something called BERT. When I say they, I mean Google. BERT, which is bidirectional encoder representations from transformers. That's what it means. It's just a model called BERT. It's a transformer model, and this and its variants. There's different variants like distill BERT and all of that. And we also have the GPT models. We have the GPT models. So we have BERT based on the transformer model, and we also have GPT, the ones that we know from ChatGPT, which are generative pre-trained transformer models. This BERT model, it is built. It is built. It is built from the transformer architecture, but trained in a different way from the GPT. This GPT is trained for generating text, right? For generating text, and but the bet it specializes in what is called masked word prediction. Masked word prediction. So just to show you quickly what that looks like. Um, okay, let me see. I think I have enough space. So in the case of, I think I should start with GPT because GPT we all sort of have an idea of what GPT how it behaves. So in GPT you can give a text like this is an example of how concise I can be. I can. You stop there and you allow the model to finish it off. Of course, it pre-processes this text, pre-processes the text. Sorry, my handwriting is terrible now because when you're so used to using the computer, um, your handwriting just fades. Okay, gets into a decoder because the GPTs they are decoder based models. We will discuss what that means later. But it pre-processes it. After it pre-processes it, this then comes out and says, this this is an example, because that was the text that we had, of how concise, I can, and then it predicts this word be. That's what it does. It generates that word be when we have given it this text. In contrast, what masked what BERT does with its masking, um, which is the masked word prediction. What you do with BERT is when you train it, you say this is n dash. You mask that word of how concise I dash B. This is what you feed the BERT model. Of course, it's going to pre-process in its own way. That's the pre-processing here. And then it feeds it into an encoder, into the encoder and encoder model here, does everything that it does. And then at the end, what the BERT actually does is it then writes this is an example. It has filled in this word, an example of how concise I can be. So it has created, it has filled in these words that were masked. So previously these were masked. So when you train it, you get a bunch of text and then you mask certain words. So you train it to try figure out, okay, I know this is n dash. It tries to figure out what the missing word is. It's pretty much here, filling in the missing word. That's what it does. So that's the difference between those BERT type of models and the GPT models. The GPT models, they will keep adding at the end like this, keep adding at the end, and then they will generate the text that way. These ones are for BERT, they are doing what is called mask word or missing word prediction. This unique way of training BERT, it equips the BERT model, the BERT model, with great strengths in text classification. Text classification. I remember when I was analyzing some news articles and I wanted to classify before GPT in 2019. To classify those news articles, I was using a BERT model. Twitter, right now probably they've moved to transformer-based models, but Twitter uses or X uses or used a BERT model to classify if something is toxic, if content is toxic. Maybe now they've moved to better models, but the BERT model the BERT model is what they were using. I said I made a mistake when I said they were using a transformer model. No, I meant what I meant is maybe they are using a different version of a transformer model because the BERT is a transformer model. But I think yeah, beginning of end of last year they were still using a transformer because Elon Musk open sourced the Twitter code, so you can read it and you actually see where it uses this BERT model to classify if a tweet is toxic or not. GPT, on the other hand, it focuses on the decoder portion of the original transformer model, as you can see here, and it's designed for tasks that require generating texts. So feeding text, it gets decoded, brings it back, feeds it again, creates new words, creates new words, creates new words. It just focuses more on this decoder portion. And that is good for things like machine translation. Machine translation, translations, summarization, really, really good at that. Fiction writing, when it generates fiction writing code, all of those things. These models are also good at things like zero shot, what is called zero shot and few shot learning. These GPT models. I might be wondering what is zero shot and all of that. So let's just give quickly an example here. So text completion. If we're doing text completion, this is going to be our input and this is going to be our output column, right? So if we're doing text completion, we can say something like breakfast. Breakfast is there, and we end there. And the output we will say most important meal of the day. That is the output. So that is text completion. It completed our text. Then for zero shot, if you're doing something called zero shot, it will be something like, okay, I've never given you, I've never given you any examples. I just want you to perform something. So apologies, I'm going to pause this for a bit. I'm actually receiving uh some some food right now, so I'm going to pause the recording right now.